How's it going there? Welcome to Ben's Lab again. I'm Ben, your host. I'll talk to you a little bit about life on Earth. This tree, like everything else in this park around us, the birds you've just seen and the grass under our feet, and even myself and the bugs flapping around my head, all very lucky to be here because so far as we know, Earth is the only planet anywhere that's made the hub of life. And it only does it because of a very particular set of conditions. Some of those include a thick atmosphere, an energy source in the form of sunlight, which you can see all around us, lighting up this glorious scene, and liquid water existing at the surface. You won't find it anywhere else. So life's very fortunate to have these, or it wouldn't exist at all. There's a little bit more to it than that, and I'll go into that later on the show. But what if we could make other planets like this? I'm going to talk to you today about terraforming, a process whereby a planet like, say, Mars or another alien planet can hypothetically be transformed into an Earth-like environment, so that instead of going there and me having to wear a spacesuit or a helmet, I could walk around like this and just live like we do here. And grass could grow under our feet, and there could be animals there, and agriculture, and all manner of things. So it is possible, not yet, but I'd like to talk to you about that today. So we're going to talk about terraforming on Ben's Lab. Terraforming is a process whereby an uninhabitable and barren planet can be transformed into a place that supports Earth-based life. Why go to all this trouble? Why would terraforming even be necessary in the first place? Look at terraforming as something like transforming a barren desert into a green oasis. We are surrounded by life here, and so take it for granted. It really is everywhere. On a place like any other planet or moon we can think of, conditions are so harsh and hostile that no life, as we know it, can exist. In order to render a planet fit for habitation by living things, it needs to be terraformed. In order to take you through the concepts of terraforming, I'm going to walk you through the terraforming of the planet Mars. Mars has been recognised as the closest planet to Earth in terms of composition and conditions. But to understand why Mars will have to be terraformed, it will be necessary to show you how Earth and Mars are different. After Venus, Mars is our closest planetary neighbour. Its orbit around the Sun is roughly 2 of our years, but the Martian day is almost the same as ours, at 24 hours and 37 minutes. Mars has weather and seasons which closely approximate those of Earth. Geologically and chemically, Mars is quite similar to Earth. Mars is also home to abundant water, just like Earth. Beyond this, however, Mars and Earth become quite different. Mars is approximately 1/3 the size of Earth, with only 38% Earth gravity. Earth possesses a thick atmosphere, consisting of roughly 80% nitrogen and 20% oxygen, with a few trace gases making up the balance. The atmosphere of Mars, by contrast, consists of almost entirely of carbon dioxide, and has a pressure at the surface of less than 1% of that on Earth. Mars was once believed to possess a much thicker atmosphere than it has today. The reason Earth has retained its atmosphere to this day and Mars has not is that Earth itself generates a strong and vigorous magnetic field. This field is generated by an active metal core which generates colossal amounts of electromagnetic radiation. This magnetic field prevents the Earth's atmosphere from being stripped away by a constant bombardment from the solar wind and cosmic rays. Without an active core, Mars produces no magnetic field. It hasn't produced one for several hundred million years. Any atmosphere Mars once had was long since scrubbed away by solar winds and cosmic rays, leaving behind only the very thin atmosphere it has today. Mars is extremely cold. The average surface temperature on Earth, barring extremes of temperature here and there, is 16 degrees Celsius or 61 degrees Fahrenheit. This is quite tolerable to most things living on Earth, and this benign climate is one reason life has succeeded here. The average temperature on Mars has been recorded above 0 degrees, but on average Mars is a giant freezer with a surface temperature of minus 55 degrees Celsius or minus 67 degrees Fahrenheit. For Mars to become hospitable to life, it is hence necessary that its atmosphere becomes thicker and that the planet is warmed up. Presently, no human being could survive on the Martian surface without sophisticated equipment, for example pressurized suits and breathing apparatus. But how the heck do we just give a planet a thicker atmosphere? Is it even possible to warm a planet up in a suitable time frame? The answer, as it turns out, is under our noses, so to speak. One thing we've proven to be very good at is tipping the balance of our own climate. Here on Earth, the average temperature has risen by 2 degrees Celsius. That's a lot. Humanity is headed for a crisis if this climate change continues, but on Mars, an artificially induced greenhouse effect could be beneficial. Venus today is a hellish world with surface temperatures of 462 degrees Celsius, that's 864 degrees Fahrenheit. It is wrapped in a thick blanket of heavy cloud and its atmosphere is 94% carbon dioxide. Venusian air pressure is 92 times that of Earth. The first probes sent to Venus in the 1970s were crushed within minutes upon landing on the surface. Venus is an example of how bad things could get. Mars just needs a little bit of a gentle nudge from us in order for its atmosphere to both thicken and warm up. There are several ways we could go about it. On Earth, aerosol sprays have been singled out as a source of greenhouse gases. CFCs and PFCs were once used in things from hairspray, insect spray, spray paint are all made possible by these compounds, and they've been used widely in the last 50 years. Carbon dioxide is another greenhouse gas. Produced as a waste product by every single animal on the planet, it is also pumped into our atmosphere in vast quantities by industry and other sources of pollution. Almost all mechanical transport on Earth relies on hydrocarbon-based fuels in order to function, oil and gas. Again, our vehicles all give off carbon dioxide, a waste product resulting from internal combustion. Vast factories pumping fluorocarbons into the Martian atmosphere in large quantities would actually trap a lot of heat in the form of sunlight reflecting off the Martian surface. This heat would eventually be enough to begin melting Mars polar ice. A lot of carbon dioxide on Mars is locked up in the form of dry ice at its poles. Should this ice begin to melt, a huge amount of CO2 would be released into the atmosphere. Not only would it crank out large quantities of greenhouse gases and begin heating the planet, it would increase air pressure. So, one suggestion is to add greenhouse gases to the Martian atmosphere in the form of factories designed to pump these gases, including CO2, methane, and hydrofluorocarbon into the air. Over time, and by time I mean decades or possibly centuries, Mars will become warm and wet once again as it once was. Other suggestions for warming Mars include the introduction of genetically modified bacteria, lichens, and algae to the landscape. Studies have shown that simple creatures like these are capable of surviving in harsh conditions like those on Mars. In fact, microorganisms already exist that can survive easily at very low temperatures, pressures, and in toxic environments. They are known as extremophiles. It is thought that if these creatures were to proliferate on the Martian surface, they could contribute to the production of greenhouse gases. An added bonus of having these organisms spread is that they would reduce the reflectivity of Mars. On Earth, one factor in climate is albedo. Albedo is a measure of a planet's reflectivity. If albedo is high, this basically means that a lot of sunlight, and thus warmth, is reflected back into space. Regions on Earth, such as polar or snow-recovered regions, have a high albedo for this reason, and it is one of the reasons why they are so cold. Darker regions on Earth absorb more sunlight. If you walk barefoot on an asphalt road on a hot day, it's really hot. This is because darker colours absorb more heat, and that's why we're often told to wear bright, reflective clothing in hot weather. Try it out for yourself one day when it's hot. Try on a white shirt and then a black or dark shirt. Which one do you think will become hotter? The same principle applies to heating Mars. If the surface can be darkened by the introduction of dark material, dust, dark coloured microorganisms, etc., this would go some way towards heating the surface. This approach will be extremely slow by itself. It is estimated that it will take at least centuries for darkening the surface to have a noticeable effect on temperature. In conjunction with pouring greenhouse gases into the atmosphere, this process may be sped to 60 or 70 years. However, in conjunction with other solutions, things can be sped up even more. Arrays of giant mirrors placed in Martian orbit have been proposed as a means of melting Martian ice caps. Reflecting sunlight from space, they present a fairly speedy solution to the problems both of adding pressure to the atmosphere and providing liquid water, which would eventually form lakes, rivers, and oceans. Climate on Earth is driven by heating and evaporation of water. The presence of liquid water would allow introduced life from Earth to fare better and would also lead to a true Martian climatic system. It is estimated that bombarding Mars with 10 1 billion ton asteroids rich in compounds such as ammonia would raise its surface temperature by 10 degrees, as well as substantially contributing to air pressure. It would introduce water and indirectly oxygen into the atmosphere. The impacts themselves would contribute heat. The ammonia in the asteroids contain nitrogen, which makes up 80% of our own atmosphere. Many asteroids and other astronomical objects such as comets contain vast amounts of water ice. This would be an effective means of bringing water to Mars. It has even been suggested that much or all of the water on Earth came from outer space in this fashion. With present technology, these solutions to terraforming Mars are within our reach, or will be soon. However, they are all just a start. Mars is still no use to us if we can't breathe its air, right? Well, introducing oxygen to the atmosphere would require the introduction of plant life. Plants would thrive on a hypothetical Mars where air pressure has been raised to something approaching that seen on the tops of high mountains. The atmosphere would now be warmer and wetter, but still consists of mostly carbon dioxide. Indeed, plants would thrive, but plants are not known for moving quickly. Oxygenation of Mars using plants in this manner would take about 10,000 years. But conditions would now be more suitable for human life. With a thin atmosphere and now more suitable temperature range, humans can move freely on Mars without using bulky spacesuits, needing only oxygen masks and canisters similar to those used by mountain climbers on Earth. This, in my opinion, is significant progress. I can already imagine myself there,